So in this video, I want to talk about generalizations of the divergence theorem. So we've seen over the last few videos that with the divergence theorem, on one side, I have this triple integral over this region D of the divergence of a vector field. And what that's equal to is this surface integral over the surface that encloses that region. So it's the boundary of that region where I'm doing the integral of this f dotted with my normal vector function. So Green's theorem has a very similar structure. If I flip it back a few pages to Green's theorem, well, on one side I have this integral of divergence. It's the double integral here because my region is this two-dimensional region. And on the other side, I get this integral for flux. So I got my vector field dotted with my normal vector, where I'm integrating over the boundary, which happens to be a curve now. Okay, so it turns out this generalizes, and it's true even in higher dimensions. So if I flip it back to where we were in the notes, so this is true even in n-dimensional vector fields, higher dimensional vector fields. So is there a one-dimensional analog of this? Can I go down a dimension? It turns out, yeah. So what does that look like? Let's let our vector field just be a function, some component, f of x, times I hat. So no j hat, no k hat, we're just in one dimension. So then my region, because I'm in one dimension, has to just lie on like a line. I'll call this the x-axis. So my region could look like this segment here. And let's say that it starts at A and then it ends at B. So that's my region. And my boundary then, the boundary of the region, would consist of these endpoints at A and at B. So the divergence theorem, on one side, we are calculating the flux. And the flux involves taking the vector field and dotting it with the normal vector on the boundary. So at the boundary point on the right, if I draw the normal vector, well, it's got to be pointing straight out to the right. So that normal vector, this unit normal vector, it's got to be I hat. It's in the positive x direction and has length 1. At the left boundary point, that normal vector would point straight to the left. So that normal vector would be negative I hat. Okay, so if I'm going to write down an expression for flux here on one side, I know that that involves taking my vector field, dotting it with the normal vector on the boundary. And on the other side, this ends up equaling an integral over the region inside. So, well, this is a one-dimensional region. So it's going to involve just a single integral that starts at A, ends at B, of my divergence of f. And it's just dx because it's a single integral. Okay, and on the other side, I got to take this f dotted with n at the boundary points. So at the right boundary point, let's plug b into my vector field. So capital F of b. And then I got to dot that with the normal vector I hat. And then I add that to the left boundary point. So capital F, plug in a, dot that with this normal vector, negative I hat. Okay, and then well, capital F of b means plug b into my vector field. I'll get little f of b I hat. When I dot that with this I hat dotted with I hat is 1. So I'm going to be left with little f of b. Similarly, when I plug a into my vector field and I dot this I hat with the negative I hat, I'll get negative 1. So this is going to leave me with minus and then little f of a. Let me give myself a bit more room here. And on the right-hand side, I get equals my integral from a to b. When I do the divergence of this vector field, normally I'd have to do partial derivatives of the components. But here, because there's just one variable, I'll just do a normal derivative of f of x. So I can write that as f prime of x. Or I can write df dx. And then I still got that dx there at the end. So this should look familiar. This right here, that's the fundamental theorem of calculus. The fundamental theorem. Okay, fundamental theorem of calculus. What we've just shown is that it's a special case of the divergence theorem. It's a lower dimensional analog of the divergence theorem and of Green's theorem. And that's part of the power of these theorems. They connect all of these ideas, this idea that I've seen before, with these higher dimensional versions of it.